Hello everyone, welcome to lesson number 32 for BC Calculus, where we're going to talk about work. In this video, we're going to apply a little bit of physics and a little bit of what we learned back with volume. So the first thing we're going to look at here is, from physics, work is simply equal to the product of your force times your distance. And so we know that force is usually not constant. It really isn't. So what we're going to do is we're going to take this formula and we're going to incorporate calculus to figure out how to find work using an integral. So the distances that we push something, so we have a little guy right here pushing this cart, the distance that he travels it as he pushes it further, the little distances are going to be our delta x for our integral. The force that we're going to have is going to be our function. And then just like with sigma notation, if we add them all up, so we do the first force, the second force, the third force, we add them up, then we're going to use an integral. So this is what force looks like in calculus. It says find the work done when a variable force. So this is one of the easier questions. It's telling us the force is in the function of 1 over x squared, and the fact that it's variable, meaning that it's going to be changing as we move further and further along in the positive x direction, and we're moving it from 1 to 6 feet. So we're going to integrate, so work is going to be equal to the integration from 1 to 6, so this is the distance that we're doing, and again our delta x is going to represent the moments that we move, and then since it's a variable force, we can just integrate 1 over x squared. And so this is a really simplistic way of doing it. The other thing I want to do is that when we do integrate this, it's going to be 5 over 6. So this will be the answer you're going to get. And our units are going to be in pounds, feet. And that's really important because of what we're going to do a little bit later on. We want to get into units of pound, feet. It's going to be the weight times the distance. All right, so it's not always pounds, feet, but it's always a weight times a distance. So our units is always going to be a weight times a distance. Okay, so that's what we're going to do, again, for a very simplistic problem. We're going to look at Hooke's law next, and then we're going to finish one, or do one that's a little bit more complicated than example number 1. So Hooke's law basically says the force F required to compress or stretch a spring is proportional to the distance that the spring is compressed or stretched from its original length. So a really important thing about Hooke's law is this really simplistic equation that force is going to be equal to a proportion constant times the distance the spring is actually compressed or stretched. And exactly what it says right here. So it says a force of 750 pounds compresses a spring 3 inches from its natural length of 15 inches. Find the work done in compressing the spring an additional 3 inches. So the first thing that we're going to do is we're going to find what the K value is. So we're going to find out, we're going to use this equation right here, and we're going to say that the force, and it tells us right here, force of 750 pounds, so force is going to be equal to K, and this D is going to be the initial compression or stretching of our spring. So you can see that we're compressing this spring 3 inches. So this is going to be what our D is going to be. So how far have we compressed our spring? So K is going to be equal to 250. So this is our proportionality constant. And what we're going to end up doing is we're going to integrate our function. So this is going to be 250x. So this is our function now. So we're going to have our K times our x. And then our dx is going to be, again, the distance that we travel. And then our integration is going to be our initial and then where our final is. So we've already compressed, using this 250, we've already compressed our spring 3 inches. So we're going to put a 3 down here. And it's going to ask us to find the work to compress it an additional 3 inches. So we're already 3 inches in from our 15 inches. We want to go another 3, so we're going to go ahead and go to 6. So this is how much our spring's been compressed at the end. So 3 plus 3 is obviously equal to 6. And then we're going to use our fundamental thermocalculus, and we're going to get that this is going to be, the force on this is going to be 3,375, and then our inches, and then it's going to be pounds, or pounds inches. All right, in this case here we have inches for our thing, and this is our pounds. So that is going to be our next example. And again, notice that the units are going to be, again, in weight and then distance. So let's look at a little bit more challenging work question that you guys can see right here. Now, this is very, in my opinion, it's very wordy. There's a lot of stuff going on in this, but it's just really helpful to kind of figure out what we need to do with these problems. So it says a tank in the shape of a right circular cone is filled with water, or full of water, as you guys can see here. Here's our cone. If the height of the tank is 10 feet, so our height is 10, and so usually what I end up doing is drawing a cone, and I just do that this is going to be 10 feet, and it has a radius of 4. So I'll go ahead and just, this is usually how I start my problem out. And we're going to do it in the next video. I'm going to do another one of these where this is not drawn, so I can show you guys kind of the idea. But this is all the information that we're going to need to solve this problem. Find the work done by pumping the water over the edge of the tank. So it's the first thing we want to do is we want to know that it's going to be over the edge of the tank. Sometimes it's going to say 5 feet over the edge of the tank, or 2 feet above. So it's really important that we just want the water over the top. Assuming that the density of the water is given to you in 62.5 pounds per feet cubed, what we're going to find this actual work, right? So we want to find the work done pumping all this water out, given that the density of water is going to be equal to 62.5 pounds per feet cubed. So the first thing we're going to do is we're going to take into account the equation that we have, that we talked about in example number 1, that work is going to be integrated from A to B of our force, and then it's going to be our distance. So our force is going to be how much our water is times what our actual volume of this is going to be. And so that's really the idea of this, is that we want to take into account how much is it and the volume that we actually have. And so we're going to manipulate this. We're going to manipulate this into something that we can easily do. And then the distance being lifted, we also have to take that into account. All right, so not only how much does it weigh, what the volume of it is, but how far up are we going to do it. So we have to take into all these accounts, and we're going to talk about that all in this video. And we're going to do another example in another video for this as well. And then A and B is going to be the position of the fluid. So where is it? Is it full? Is my water full? Is it half a tank? Where's my water? Where's my lowest amount? Where's my highest amount? So the first thing we're going to do here is, if you guys look at what this is, if we were to, again, think about this as a circular cone, if I take a little piece like we've done with volume and with area, if we start rotating this around, you guys are going to see that these are going to end up being circles, right? These are going to end up being little circles. So this is going to be more so circles, but they're going to end up being really tiny a cylinder. Like there's a really tiny, tiny, tiny little cylinders of water that we're going to have here. So the volume is going to be the volume of our cylinder. And for these cones, it's always going to be that. So your volume of your cylinder is going to be pi r squared times our height. And so this is what we got to all figure out. So as you guys can already see in the example, we've already figured out that the force is going to be, again, the volume times the weight. And we've already given what the weight is. So our force is going to be, I'm going to go ahead and multiply the weight first. I'm going to do 62.5. And then we want to go ahead and do the rest of this. So we're going to do a pi. So what is the radius? The radius is actually going to be the distance from here to here. This distance right here. This is going to be our r. All right, this is the radius of our cylinder. Because again, we're looking at these are cylinders. So this is going to be the r. And so how do I find this distance? Well, this is what I always suggest. And again, when you guys see another example, I always draw this where my corner of my cone is on the origin, and it goes along the y-axis. Because if I can find the equation of this line, right, I can subtract the equation of this line. And this is what we did in volume. So it's going to be our right curve minus our left curve. So I know that the point goes through, I know that this line here goes to the point 0, 0, the origin. I also know that it goes to the point 4, 10. So I can use point slope. I can say that point slope, so y minus 0, well actually I can first of all find the slope of my line. So I know that the slope is going to be 10 minus 0 over 4 minus 0. So my slope is going to be 5 over 2, or again 10 over 4. So the equation of my line is going to be y minus 0 equals to 5 over 2x minus 0. As you guys can see, it's going to be equal to y equals 10 over 4x. But again, we're subtracting right minus left. So we have to rewrite this and we have to solve for x. So you guys can see that that's what we're going to use right here. So our radius in this example is going to be equal to 4 over 10 y, which again would just be 2/5 y. And again, I just solved this equation for x. So our radius is going to be 2 over 5 y squared. And then the next thing we need to do is find our height. Well, what's going to be the height of this thing? Well, the height of this thing is actually going to be the delta y. Again, this is going to be, the height is this little guy right here. How high is this? How high is our cylinder? And so it's going to be our change in our y. So height is going to be the change in y. And then distance is how far we want to travel. Well, we're filling this tank with water, and right now our water starts at 0 and we have it filled. It is full of water. It's full of water. It's not half water, it's full of water. So our distance is going to be 10. So we're going to travel at 10. Now, so the A and the B are going to be 0 to 10. So let's actually write that out first. So we're at the bottom of the column and we're at the top of the column here. If this has said half filled with water, this would be 0 to 5. Be 0 to 5. So displacement. So this goes back into like the shell method. So if I want to go over this, so this is kind of like thinking about if I want to rotate around this line right here, y equals 10. And remember that from the shell method, this distance here from the x-axis to our rectangle is going to be y. So we want to find out what this distance is. And so this distance is going to be our displacement. How much do I need to take this rectangle and take it out of the tank? So this distance is going to be 10 minus y, which is what you guys see right here. And again, I'm going to do another example for you guys, a lot of examples of this so you guys can see it. And so we have everything that we need in order to solve this work problem. So we're going to go ahead and integrate, and we're going to integrate from 0 to 10, and we're going to plug all this stuff in. So we're going to go ahead and do 62.5, we're going to do pi, we're going to do 2 over 5 y quantity squared, we're going to multiply it by 10 minus y, and then we're going to do dy. So this is the correct setup in order to solve the problem. Now, one thing that I want to suggest to you guys is you want to look at your units. You want your units to be pounds per, in this case here, pounds for feet, or pounds feet. So this is the easy way to do this. Well, this is going to be pounds per feet cubed. Pounds per feet cubed. This is going to be, because this is our radius is actually simply going to be in feet, right? Our radius is going to be feet. So we have a square of them. So we're going to multiply by feet squared. This is going to be in feet, right? How much feet do I move up the cone? And the delta y is also going to be feet. And so if I were to multiply all these things together, you guys are going to see that the feet cubed cancels with all of this, right? The feet squared and the feet, and so I'm left with pounds feet. So you know that you have not missed anything here, that everything works out, because if I start simplifying this down, I'm going to get pounds feet. All right, pounds feet. And so if you were to plug this into your graphing calculator, because this is definitely a calculator problem, you're going to get that this is going to be 26,179 feet pounds, or pounds feet. It doesn't really matter which one it is. All right, so I know that was a lot. I think that this question was very busy. So we're going to come back in video number 2, where I'm going to show you guys how to do this problem again with a lot less busyness. And then we're going to do a couple more to make sure that you guys feel comfortable with this concept. So I will see you guys in the next video.